Thanks for the invitation. It's a pleasure to be here. And thank you for coming early in the morning. There will be no number theory in this talk. So sorry about that. But there will be maybe questions that number theorists will be able to answer. Let me describe the basic question. So suppose you take a random unitary matrix, and we have already seen in this conference, and it goes back to Diaconis and Shashahani, that the high traces, or the traces of this matrix, behave like Gaussian random variables, in fact, in a very, very strong sense. Namely, if you take the trace, for example, a single trace like that, and you compute its moment, or you compute a word in moments in these traces, so they are parameterized by k, and by word, I mean you take either the variable or its complex conjugate, and you create a product of those, and you compute the expectation. As long as the sum of powers is smaller than the dimension, you have equality with the moments of Gaussians. So it's really Gaussian in a very, very strong sense, not just asymptotic as n goes to infinity. And then, of course, I don't need to explain to this audience that such matrices have some conjectural and not conjectural links with Riemann zeta function. In particular, some of the interest in these matrices started from that direction. And about 25 years ago, people proved that the log determinant is a Gaussian with a variance which is proportional to log n. And shortly after, work of Keating and O'Connell, and then of Wiand at Stanford, had multidimensional extensions. Namely, if you look at the log determinant at several points, and you ask, how does it look? So we said each one of them is Gaussian asymptotically. But what you get is you get a Gaussian vector whose covariance is log correlated. So maybe it's good to define what log correlated means. It means that covariance is proportional to log of 1 over the distance between points. So the closer points are, the higher the correlation is. Okay? And of course, this is not true if you take the points too close. If you take two angles, theta and theta prime, whose distance is 0, it's not, the covariance is not going to be infinity. But as long as you are over a certain scale, and this relevant scale here is 1 over n, you do see a log correlated structure. And it also manifests itself if you integrate this field. So you think of this log of the characteristic polynomial as a function of z on the unit circle. And if you integrate it against a test function, you get a Gaussian random variable whose variance is what you would predict for Gaussian fields with this correlation. Okay, and maybe I should say that this, from my perspective, was worked in the last decade or so on log correlated field, and in particular on their extremes. That begs the question, what are the extremes of such a field? Of course, I'm not the first one to ask these questions, but before describing what were the conjecture and what is known, let me say one word. So I said that it is known for a long time that this log determinant or log characteristic polynomial is asymptotically a log correlated field, and you could ask, what would happen if this field were truly a Gaussian field with this kind of covariance? So here is a statement. Suppose I have this covariance here, which is log, plus some perturbation, which is bounded and continuous, say on the unit circle. So throughout this talk, nothing is specific to the unit circle, but throughout this talk, I'm going to speak only about the unit circle, which is where this behaves like a log correlated field. Then there's a very general result for Gaussian log correlated fields that tells you that if you ask about the maximum of this field, then it converges to a very specific object. So it converges to a sum of 3 terms. The leading order is log n. Then there's a correction of order log n. And then you have terms of order 1. There's a certain constant. There's a Gumbel random variable. And there's another random variable z, which is independent of the Gumbel. And that's a general result. So if you give me a log correlated field on the unit circle with covariance that behaves like that, this will be the maximum. Now I have to explain several things here, and I will. Why do you get all these terms? But maybe at this stage, I should emphasize what is a Gumbel. So a Gumbel is just this distribution function. And the log of the Gumbel is related to the exponential random variable. That's really what you should think about. So log z is going to be related to an exponential. Okay, so back to our circular ensembles. So we take a matrix, random unitary matrix, and we look at the characteristic polynomial on the unit circle. And mn star is going to be the maximum of that characteristic polynomial. Okay? So by analogy with a log correlated story, you would say, well, mn star should have the asymptotics I just described. So it should behave as mn star divided by log n should converge to a constant. There should be a log-log correction that converges to 3/4. And then there should be fluctuations, which are Gumbel plus something. That's what you should expect. And okay, so this was put on a firm precise statement by Fyodorov, Hiary, and Keating about 10 or 15 years ago. And they conjectured exactly that it will behave like that, with a very explicit form of this Gumbel plus something. Namely, their conjecture is that the something is itself Gumbel, a log Gumbel, actually. No, sorry, the something is itself Gumbel. Okay? So that's the conjecture. And you say, but we converge to Gaussian, and we know that this is true for Gaussian, so what's the big deal? I mean, this. But then you realize that if you asked about the minimum instead of the maximum, which for Gaussian would make no difference whatsoever because of symmetry of the law, the minimum is minus infinity because there are zeros on the unit circle. So it certainly cannot be just a convergence to Gaussian tells you that this statement is true. Okay? So there has been progress in the last decade towards, yes?
The Gaussian thing, you also had this thing that came from microscopic fluctuation.
So there is a constant here. There is a constant. There's always a constant, and I'm not paying attention to it. C is a constant, yes. C is a constant, and I'm not paying attention to it, although one could. In fact, the conjecture has a precise value of the constant, which in the proper scaling I think is 0, but okay. So there has been progress on that. And the first work that did significant progress was by Argan, Bellius, and Bourgade. And they identified the one. Shortly after, with Elliot, who is here somewhere in the audience, I believe, yes, we identified the minus 3/4. And these two works, while they were the first in this direction, they were with a wrong method, in a sense. And they used, in an essential way, the fact that beta equal 2. Certainly, the work of Paquette and myself, this was absolutely crucial in the computation because it used the determinantal structure of the eigenvalues. And in particular, speaking about this result of Paquette and myself, it is based on computing exponential moments by using the determinantal structure and expressing the moments of determinants as themselves Toeplitz determinants. But shortly after this works came an idea which kind of made the whole thing much more precise. And this idea works for any beta. So from now on, I will consider a model of eigenvalues, because the log determinant, after all, is just a function of the eigenvalues. So we are looking at eigenvalues whose joint distribution is proportional to this expression. Okay? So this is a so-called C beta E, as CUE was a random Haar unitary, and with beta equal 1, it's not a random orthogonal matrix, but it's related to that. And for arbitrary beta, this makes sense. This is a joint density, and you could ask the same questions. You still have a log correlated structure, and you could ask the same question. And the work I'm referring to is this work of Shaibi, Madul, and Najnudel, where they showed that the error term, after you subtract the leading order and the second log-log correction, the error term is of order 1, in the sense that this is a random variable whose law is tight, namely that the probability that it is larger than a large constant is small uniformly in N. Okay? So that's the statement. And the topic of this talk is that if you look at Mn star minus this quantity, so you look at this order 1 variable, it does converge to a Gumbel, to the sum of a Gumbel random variable plus another random variable. This other random variable, actually, we expect it to be Gumbel, and the proof maybe will appear. So there is a sketch of a proof, and I believe that this is true. Okay, so how do you do all these wonderful things? So was there a question? No. So the key step is to move from a description in terms of the joint distribution and properties like that to representation in terms of orthogonal polynomials. So there are two steps to this. First, there is a representation of the C beta E matrices that have the joint distribution like in C beta E in terms of certain 5 diagonal matrices, which are built from a sequence of independent random variables. So for those who have not seen, there is a beautiful theory of orthogonal polynomials on the unit circle. There's an encyclopedic book by Barry Simon that describes this theory. And this is a particular random case where you can give a nice representation, and once you have this 5 diagonal matrix, you can ask about the spectral measure associated with that matrix. And this spectral measure has orthogonal polynomials associated with it. And there is a recursion for the orthogonal polynomials. And all the information is in those orthogonal polynomials. So let me write the recursion. This is a recursion. So this is kind of a black magic that, of course, you can prove it, but it's a very nice observation that you have this kind of recursion. So phi k star on the unit circle is nothing but the adjoint multiplied by z to the k. And the important thing in this recursion is that you have these variables alpha, which are called the Verblunski coefficients, and they are independent. Okay? So those are orthogonal polynomials associated with the invariant measure, with a spectral measure. And the point is that you can write the determinant as a combination of phi n and phi n star using an extra randomness, an extra single random variable, which is uniform on the circle. So you have a representation of your determinant as taking the solution of the recursion and then doing some operation at the very end. Okay? So this is what we have. The psi that I wrote here is a certain angle that relates, when you are on the unit circle, it relates the phi n star and the phi n, and the imaginary, in fact, it's related to the imaginary part of phi n star. Okay. And it's not very hard to convince yourself that if you're looking at the supremum of the log of the characteristic polynomial, then if you're interested only at order 1 errors, it's enough to look at the supremum of phi k star, of log of phi k star, instead of looking at the determinant. So you can completely, if you're only interested in order 1 error, you can completely forget about the last equation. Phi n star, thank you. This k here, yeah, that's a font, as we know. It's the wrong font. So this is phi n star, yes. Thank you. Okay, so those are the recursions. And now let's look a little bit closer to these recursions. So I rewrite the recursion in terms of this psi. It's not very hard to convince a bit of algebra that the psi itself satisfies a recursion of this form. And the important observation, the first observation to note, is that if you look at this right-hand side here, and even if you condition on psi k minus 1, so you condition on the solution of the recursion at step k minus 1, the distribution of this log does not depend on psi k minus 1. Because alpha is independent of the past, and the angle, alpha has a uniform angle on the unit circle, it washes out whatever information you have on psi k minus 1. So it means that the log of phi k star is actually a random walk. Not with IID increments, but with completely independent increment, not approximately and not nothing. The Gaussian will come from summing a lot of independent random variables. Okay? And the marginal, therefore, of the log is essentially Gaussian, right? It's a sum of lots of IID random variable, and you can compute the variance, and that's what you get. 2 over beta log n. Okay? Very good. So, yes, the font also extends to spelling errors. You can also try to ask yourself, okay, that's very nice, but if I want to say that it's a Gaussian log-correlated field, I have to look at different angles at the same time. I have to look at joint distributions. And there, the argument I just made does not work. It is not true that the joint law of 2 points is exactly Gaussian, or is satisfying, is jointly Gaussian. A priori, this is not true, because the increment is now a correlated increment in a complicated and nonlinear way. It's not just an independent vector that is completely independent of the past. So, so here comes where you should ask yourself, okay, how do I have a structure that is simpler and that I can understand and maybe copy into this game? And the answer is yes, and this is a branching structure. So I want to explain that here. So I'm going to digress now, and maybe, sorry, I just realized that I skipped something that I wanted to say. There are, of course, also links to, for those who have worked on that, to Gaussian multiplicative chaos. This is all related to this circle of ideas. I'm not going to talk at all about multiplicative chaos, although it will show up a little bit later down the talk. So we have in probability a model that was that goes back 100 years of branching random walk or branching Brownian motion, which also exhibits similar structure. Namely, you have lots of vertices. I'll describe the model in just a moment. You have lots of vertices or sample points, and each one of them is separately Gaussian, but the correlation structure is non-trivial. And what is the model? The model is the following. Take a binary tree. You'll start with a binary tree, and on each edge, write an independent random variable, okay? So we have a tree. On each edge, we put a Gaussian random variable of variance 1. So obviously, at the bottom I mean at depth n, you will have a random variable of variance n if you sum up all the variables leading to that vertex. So we call the variable SV, the variable at the bottom of the tree. And this is the sum of the edge weights along the geodesic connecting to the root. Okay? You maybe have noted that I have used here a different font. This actually is on purpose. So every time I write little n, it is going to be log of capital N. Okay? And the reason is, if you think a little bit about the structure, the number of vertices I have at the bottom, at depth n, is exponential in n. And I told you that the natural scale that we are shooting for is 1 over capital N. So I need essentially log of capital N, which is little n levels. But okay. So now we can look at the maximum. And if things were independent, what we would get, this is an undergraduate exercise, right? I ask the maximum to be smaller than something, that's some mn. Then because of independence, I would have it to the power 2 to the n. And what you can check is that this gives you a Gumbel plus this mn, and mn should be n minus 1/2 log n. Okay? But this is the incorrect answer for the model of branching random walk, and work that has been done starting from the 80s shows that in fact the centering changes because of the log correlation. So two changes happen. One is this 1/2 becomes 3/2, and second, the Gumbel becomes Gumbel plus something. And the way to prove it is a sophisticated version of a second moment method. I don't have time to get into that. But the basic idea is that because of the tree structure, if you look at that random walk that we talked about, so you have a random walk along a geodesic, and you ask yourself, what value can it take in the middle of the way, the answer is that it cannot go much higher than the straight line connecting to the bottom. And because there are just not enough points in the middle of the way. If you go at a depth t from the root, you only have 2 to the t vertices and not 2 to the n like you had for independent variables. And this puts constraint on the walk, and in particular, it forces the walk to be below a certain straight line that leads to the maximum. So I know it is vague, but this is the idea. So now I want to go back after I have explained what happens for branching random walk. I want to go back to the C beta E and try to explain the ideas that happen. And of course, I should have said it in the very beginning. Of course, there are analogs of this whole procedure for the Riemann zeta function through the work of Argand, Bourgade, and Radziwill, and also Sound. But I'm not going to talk about that at all. Okay? But many of the ideas here you can find analogs in the work. Of course, the tools are completely different. Okay, so the first thing, which already was done by CMN, is to say, well, at the end of the day, the determinant is a polynomial, and polynomials of degree n cannot oscillate too widely. And in particular, since it's a trigonometric polynomial, if I give you n points, in principle, I know the polynomial, capital N points, I know the polynomial everywhere. So if I'm interested in the maximum, I don't need really to look everywhere. So this is an interpolation lemma that says that if you take instead of capital N point slightly more, or in this case a polynomial of degree k, and you take slightly more than k points, so in this case just root of unity, you can control the maximum of the polynomial, the global maximum, by the maximum on this lattice. So it's enough to consider a lattice. And that's what we are going to do from this point on. So remember, we're interested not in the maximum, but not in Q, but in log of Q. So any multiplicative error which is close to 1 will not affect convergence results. And there is a local version of that. So this idea of using this is already in the CMN paper. If you want to do the maximum, you need to localize. So it's something like, if I want the maximum in a neighborhood, I can look at the lattice in the neighborhood as long as I control the points that are far away, that they are not too big. Okay. The second important step, so the first step, we reduce to a lattice. We are at least in analogy, formal analogy with story of the branching random walk. The second step is to say the recursion process, so I write here phi because I'm interested both on the real part of the log of phi star or on the imaginary part. This process is continuous at scale k. So if you're looking at phi at 2 to the k, it's continuous at scale 2 to the minus k. So at the end, the process itself at step n is continuous at scale 1 over n. And the reason is that the phase, the phase, which is the imaginary part of log of phi n star, which is a psi that appeared in the recursion for the angle, has a deterministic drift, which is theta times n. So if I have two angles, so what do I mean by that? If I do all the phases relative to angle 0, and I'm looking at angle theta, then the phase of the recursion in each step is picking up a theta. So this is not much in the beginning. If theta is 1 over capital N or 1 over capital N to the power 1 minus epsilon, as long as you didn't do N to the 1 minus epsilon steps, you don't feel this drift, and things are more or less going together. Once you reach that angle, things begin to unravel and things begin to decouple. So this is a crucial part. Again, already in the proof of tightness, you need something like that. And this tells you that you have approximate decoupling. Namely, the recursions, if you look at two angles, theta and theta bar, whose distance is 2 to the minus k, there is a common trunk up to generation 2 to the k, which correspond to variance k. And after that, things decouple, which is exactly what happens for branching random walk. You have a common trunk. If you have two vertices at the bottom of the tree, you look at the common ancestor. There is a common trunk leading to the common ancestor. And after that, things are completely independent. So this is a story here. Because of these recursions and because of this deterministic drift, you will have a common part up to a distance which is a natural, or up to a distance in the recursion which is related to the depth. And after that, you will have decoupling. So what I've done in the last 10 or 15 minutes is to convince you that things look like branching random walk. So now I want to explain what are the obstructions. Why is that not quite true, and why you still need to do something. So first of all, so in the story of branching random walk, we have very nice and strong tools at each step. First of all, in the beginning of the tree, if we condition on what happens in the first, let's say, 10 levels of the tree, what happens below is completely independent. So the increment for different vertices at level 10 are going to be completely independent. And furthermore, the values at that 10 points are going to be you understand them very well because they are themselves a branching random walk. So that's a macroscopic picture. Here, the macroscopic picture is very different. The things are not really discrete. They are not piecewise constant. It's very different. The second thing is that at microscopic scales, again, we are very far from a branching random walk structure. And locally, you have correlations that are not at all, they are completely smeared out. And the third thing, which happens if you want to do the convergence, you don't really care about the maximum of phi, but at the end of the day, you need to take a maximum over a neighborhood, over really the continuous process phi. Let's say I tell you that phi is a high point, that a point theta, a certain theta is a high point. You need to take the maximum in a neighborhood of that point, and that involves understanding the process not just at that point, but the continuous process in the neighborhood of that point. So you need to carry with you some description, not just of the maximal point, but of the neighborhood around it in order to get the determinant, because the determinant is not phi. The determinant is some function that you build from phi using an independent random variable. Okay. So the first 2 points already appeared in the study of the maximum of log-correlated Gaussians that I referred to in the beginning of the talk. Because for log-correlated Gaussians, there is no branching random walk behind. And there it was resolved using the Gaussianity and in fact, using the fact that Gaussian processes can be compared. If you give me two Gaussian processes, everything is determined by the covariance. And if I have a certain comparison between the covariants, I can compare the maxima, which is not present here. So here we only have information on covariance, but it doesn't allow me to compare the processes themselves. Okay, so let me describe how to handle things. First, the macroscopic scales. I promised you there is a random variable that will appear in the limit theorem, so let me describe it here. So look at the following object. Take the log of phi star. Phi star is a solution of the covariance. Remove a certain centering. So this centering is exactly what would happen. It's the right scale. And then multiply by the same variable here, taking only the positive value. Those who have worked on Gaussian multiplicative chaos would recognize that this is related to the critical GMC. This is the analog of what is called the derivative martingale. And now, look at the total mass of this object. So you think of this object as a measure on the unit circle, and just look at the total mass of this measure. So this is a random variable, which is close to a martingale. In fact, if I did not have, if I did not have the plus here, then it would be a martingale. But the plus here does not really matter because we know that the log of phi star with the correct product is actually going to be log n or log k behind the log k. So this quantity is going to be with extremely high probability anyway positive. Okay? Of course, the positive part prevents it from being a martingale because at time 0, this object is 0. But it is not a martingale because of an event of low probability. And this turns out not to affect convergence. So the theorem is that there is an almost surely random variable, B infinity, and a measure D infinity, which is non-atomic, such that you have convergence in distribution of these things. And the only angles that contribute to D infinity are angles theta, where phi k star, for k along the way, is close to the maximum. Okay? So this is a first theorem. The proof is not particularly hard. But the point to note is that the random shift eventually is log of B infinity. Now, in the case where this was not present here, and the constants here were slightly different, Najnudel and Lambert and Najnudel have just proved last summer that this object, or this total mass, converges to an exponent, the log of this. This total mass converges to something, an exponential random variable. And if that were the case here as well, then you would get a Gumbel for log of the total mass. And we believe that you can take the proof, modify it appropriately using some of the estimates here to get it for the derivative martingale. Okay.
Gumbel does not come at all from a maximum of a.
No, okay. The Gumbel, the other Gumbel does come from that. So I said you have Gumbel plus something. The something is related to the macroscopic structure, as here. As an accident of nature, if you believe of accidents, or as a miracle, if you believe in miracles, or whatever. Here it happens to be Gumbel, but a priori there is no, I don't have a good explanation except for, the proof does give an explanation, but okay. What about microscopic obstruction? And maybe this is a point that, if, especially for the number theorists, where I believe that the number theory story is very different. I mean, the Riemann zeta function story is very different from the story that I'm telling you here. So at the end, what we want to do, I said, there are the macroscopic part I dealt with, and there is a microscopic part, which eventually translates to a constant to the constant C that appeared in the theorem. So we can look at the increments towards the bottom of the tree, in the microscopic scales, which essentially means let's condition on what happened up to recursion n, capital N divided by some big constant, K1. So you have still fluctuations of order 1 at the bottom of this tree. What happens in the branching random walk story is that these little subtrees that are hanging out there are completely independent. If I condition on the value at scale little n minus log of K1, this object, these increments are completely independent between the vertices. And here this is definitely not the case, but what saves us are two facts. The first fact is that we only need to look at points where the value that you achieved is already high, and there are not that many such points. And we want to understand the whole subtree, which means we want to understand the whole trajectory of phi n at this level. And the precise, I wrote meta theorem because I don't give the precise definitions and conditions, but the statement is the following. If I look now at those pieces of trajectories, conditioned on the solution of the recursion at level capital N divided by K1. Okay? So this corresponds to, in whatever the composition of Riemann zeta that you would like to do, this corresponds to large primes. And the point here is that conditioned on these values, if I look only at high points, and I now look at the two-dimensional object, the value theta j and the increment delta j. Delta j was the increment that is written at the top. This collection of pieces of paths in the space of 0 to pi cross continuous functions converges to a Poisson point process. Okay? It's a very strong statement. I don't expect it to be true in other situations. It's not needed, but this is the only way that we could do the proof. We prove this rather strong statement. And not only that, but you can identify the path, this family of paths, so this is really a path, as a solution of a stochastic differential equation, a system of stochastic differential equations that are a function of theta. Okay? So we have a good description of the bottom. That's a key of the bottom of the recursion. And the proof is, so you may wonder, how do I get a Poisson process? After all these recursions are driven by the same random variables. Right? In each generation, I have a single random variable that doesn't depend on the angle. So why do I get some kind of independence at the bottom? And this is a very strong statement of independence. So the answer is that you have a lot of them, and you're taking combination of them with weights that are rotating at different speeds. So it's like you're taking a sum of Gaussians multiplied by coefficients, and the coefficients are like cosines of different angles. So this you compute, you get a CLT at the limit, and you compute the correlation. You see the correlation is 0. In fact, it's like decomposing a bunch. If you count dimensions, there's exponentially many variables and exponentially many points. So the dimensions match, and in fact, it's just a change of basis. You're taking your original Vrblunsky coefficients, which are exponentially many of them, and you're changing a basis by these recursions. This is very roughly the idea. And what you can prove is this very strong result. So this is a part that really getting an analog of that in the zeta case would be great. So if the angles are mesoscopically separated, you can construct your Vrblunsky coefficients in such a way that these guys are completely independent, up to an error that is negligible, up to an additive error. So once you have independence, a Poisson process is not far behind. Okay, and the exact technical tool to do that is you don't have independent random variable, but there is a beautiful result in probability theory that allows you to prove Poisson limits for dependent variables if you know that each variable is dependent only in a small number of others. Doesn't matter what the structure is. But if you know that each variable depends only on little order of the total number, plus you have some control on moments, you have a Poisson limit. So this is the idea here. And as I emphasize here, to me, this seems the hardest element to generalize. And I want to emphasize it is really not necessary. What you really would need is, instead of this Poisson convergence, is that condition on the early part, you have some kind of ergodic phenomenon that somehow averages behave correctly. Once you have a Poisson process, that's of course correct, but in general, not. Okay, so that's the end. All the rest are kind of too complicated to describe now. So, okay, thank you.
Yeah, thank you for the talk. Just to go back to your point at the end, can you conceive that a proof for CUE that would use, instead of the phi decomposition, the traces of the powers, which is more analogous to what we have for zeta? And then maybe that can help go over the hurdle of large primes being not independent.
I'm not maybe. So I don't know. The problem. The problem here would also be that if you look at the high traces, you have the same high traces entering at different points. So you again come to a situation where you have a weighted sum of these high traces. And it's very you would have to prove a statement like I said before, that if you take 2 points that are macroscopic, they are exactly independent, not approximately independent. That you can construct them with some uniform error, uniformly small error, such that points are exactly independent. At least if you wanted to prove, I'm using here 2 moments suffice. So 2 moments suffice require essentially exact independence or very strong control on the conditional law, which is impossible to achieve in practice. So if it's not independent, you have to tell me, I give you all the combination of traces at a different angle, mesoscopically separated, but at all of them, and I want to understand the combination in one neighborhood. And to claim that you can construct your process, or you can construct your random variable in such a way that these guys are exactly independent. Okay? They are not exactly independent to start with, so functions, if you give me the whole trajectory, they are certainly not independent, because if you give me a piece of the trajectory, I can go back and read the function. So it's important that we are looking at a lattice of points, and it's important that we are able to do it at once for all of them. But maybe it's doable, yeah. So that's, sorry?
It would be an intermediate step.
Right. Yeah, we can discuss it.
So the limit you get is a Gumbel that comes from an extreme value, a variety, and then another shift which happens to be Gumbel.
Yes.
And for whatever reason.
Well, this is not yet a theorem, but I believe so.
Okay.
Another shift, which we believe to be Gumbel.
Okay. So if you look at the second maximum,
Yes.
the first should stay like the second point in a Gumbel extreme value field, and the second might be the same Gumbel if it's a shift.
No, it's slightly more complicated. So this we understand very well in the case of
that's what I'm
Gaussian
asking.
log correlated fields, and it's the same story. So the structure of the extremal process is the following. You have what we call clan leaders, which means if you look at a microscopic neighborhood, look at the maximum in that microscopic neighborhood. Okay, call this process the process of clan leaders, okay, for reasons that you can imagine. Now, this process has a simple description. Namely, it is shifted by this global shift, and in addition to that, you take a Poisson point process with rate e to the minus x. So you create a Poisson process with rate e to the minus x, you shift it by this global shift, you got yourself what you call the Gumbel story. So you had the global shift, which was a thing, plus this. But now each of these guys have a local maximum next to it, a decoration. So what you get is you have this story, and each geyser has attached to it a cloud of followers, his cousins, his second cousins, etc. And what you get is this whole mess, right? You have the superposition of these processes.
More than a question, a remark related to your question, Gerard. For this accidental Gumbel, the first place it appeared is actually in the work of Fyodorov and Bouchot. And there is no intuitive explanation, it's really a calculation.
No, but also they didn't know it's Gumbel. The fact that it's a sum of two Gumbels was discovered later. They wrote a Bessel function.
Yeah. So they get a Bessel function, which happens to be the density of...
Which happens to be, but
the
I
way
talked
they
to
obtained
them.
it was a calculation.
Formula,
Right.
okay, then you can put a name on it, but it's
No, but on top of it, no, but what I'm trying to say is something else. They did not know. This I talked to Jan. I mean, I'm not inventing here. They did not know that this object, which has this density, which is a Bessel function, is the density, it's a convolution of two Gumbels. They did not make this observation. This observation was made later, much later, almost 10 years later. Right.
If you look at the maximum over a shorter section of the unit circle, you expect to get Gumbel plus something that's close to Gumbel, but not exactly Gumbel.
Yes.
Are you able to reproduce that? Have you made essential use of the fact that you're maximizing over the whole circle?
So what you will get, I'll tell you exactly, even though it's not written, I can make an educated guess. And the educated guess is that you'll get not the total mass of this measure, but the mass over this smaller arc. This is what is going to be important. And it depends whether this arc is macroscopic or mesoscopic. If it's mesoscopic, it's just going to be a constant. That's it. But if it's macroscopic, then it's just going to be the integral of this measure, not over the whole circle, but over a part of the circle. And it is what it is. And I guess that the limit procedure that allows you to identify this variable. So I didn't say anything about this, but the work of Joseph, who is here, and Gauthier Lambert is essentially by approximating it from the inside and showing that a certain interchange of limits. And from the inside, they understand very well what is going on from the inside of the circle. And then they take the limit as they approach the boundary. I guess you could do it also for, right, Joseph? You could do it for a part of the circle and get whatever you get.
Yeah, but
it's not going to be Gumbel.
the explicit distribution, there is no specific form.
Sure, sure. So you can write a limit. You can say it has a certain limit that is given by exactly this random variable. To me, the fact that it's Gumbel or not Gumbel is less of an issue. I gave you a formula. I gave you a random variable. And there it will be just the integral over shorter region.
Just a follow-up on that. So when you take a mesoscopic interval and you look at your law, is it true that it's sort of erased information of the macroscopic field?
Yes. Yes.
So then do you believe that that law, I think Fyodorov told me that at some point.
This should be Gumbel.
But he thinks that it's also universal in the sense that for zeta, if you take also a mesoscopic.
This is a general thing about log correlated. If you go to a mesoscopic scale, you kind of erase. You have an extra random variable. So it depends. You have an extra random variable that is common to everybody. So you're modulating the whole thing with an extra random variable, which is, think of the tree, right? You have this long edge. If you're mesoscopic, it means you added a long edge. And this long edge can have a huge variance.
So you're saying, let's say I take zeta, I take the maximum in the mesoscopic.
You will have some kind of Gaussian variable that will modulate everything and will take over.
Okay, so
it depends on how mesoscopic is mesoscopic, but you will have a big common trunk which has a fluctuation. It depends on the angle where you look at. So you have to subtract it. If you don't subtract it,
so you said the large, so the large primes would not give you something, would give you something universal like you get for C and not something which is zeta.
if you look microscopic, yeah, I believe so.
Looks like there are no further questions. Let's take off again for a talk.